We embarked on this journey to learn more about what green chemistry is. At the start, most were wondering, what is this chemistry of color? But now, we are understanding bit by bit what are these principles, how can they help to save the environment, how can they make the environment a better place, how can we reserve our resources, how can we work with different processes and products while not getting worried about the repercussions or the toxicity or any effects of the processes, products, and the byproducts. We have covered 6 principles already. We want to learn more about the other 3. Hop on the journey and let us learn more about what green chemistry is. Someone might say, am I in a business class? No, but we're going to use the relationship from business to chemistry in that we learn more about what it means. In the business world, anyone who is investing in any venture will desire to have the maximum profit of their investment. As the businessman we have discussed about, the same should be with the person developing a product. We want to get the utmost out of the input in the process, and it should be seen in the final product. In this regard, consider our input as the investment we have put in our process to get a particular product. With atom economy as the principle, we want to achieve the maximum output from our inputs, in that we reduce any losses that may be attached to our input. To understand this better, I'll use the process of making a particular alcohol called ethanol. To most of us, we know the fermentation process of making ethanol. Starting from glucose to ethanol, we are using an enzyme to break down the glucose and to yield ethanol. But in that equation, if you are very keen, you realize that we have carbon dioxide. So it means our investments, which were put into the process to manufacture ethanol, some of them have gone into the process to generate carbon dioxide. Now, the economical way of producing ethanol would be using a route, ethene. Because with ethene and water, all the atoms involved in that process are utilized to generate for you ethanol. So meaning that process is economical. With this principle, we see that many a times we want to get the function of whatever product we are aiming to get. But usually this comes with an effect to either human beings, the environment, and also the animals, the birds, the insects, name it. But this principle calls to our attention to come and think about the repercussions of the substances being made. This principle not only tells us to think about the end product, but also the safety of the people and the environment from whatever is being put in the process. Here we are seeing that whatever syntheses are being used to make a product, however much the product itself may be fine, but the byproducts or the chemicals or the inputs used, they shouldn't be harmful to the environment or to the human beings. In this regard, we are preventing harm of the process itself, because someone might pause and say that the product is okay, but is the process clean? We're not only greening the product, but also the process. A typical example we can use is in the manufacture of polycarbonates. We'll have alkyl carbonates. All of these have different purposes, but what they had in common was the use of phosgen gas. Did you know that phosgen is really a toxic substance Remember, it has a very bad track record that was used as a chemical weapon in the First World War and was responsible for the death of 85,000 people. Imagine what it could do in case someone in the process production fumbles. They replaced it with greener alternatives. Indeed, it made these processes better. For example, the use of carbon dioxide. So we are seeing that there is research aimed to make the processes in themselves safer, because at the end of the day, a gas like phosgen or its derivatives, there is need for disposal, treatment and all that. And also the people handling the toxic substances in the process may also get hurt. So there is really need to watch out. Many a times when developing products, there are many ways in which it is achieved. And one of them is building up a product. You may start with a simple compound, but the simple compound which you have started with may lack some characteristics which you may like. And to get these particular characteristics, you may desire to add some other functional groups or atoms on the simple compound you started with. And sometimes you start with a simple compound, but it has extra details that you don't want. So you want to make it better by removing some parts. In this, you do not want the whole compound to react as a whole, but you want to use particular sites, bonds from this compound to either replace or add. The use of blocking agents, protecting and deprotecting groups, the change of physical and chemical properties, just to give us room to manipulate the compound structure, should be really minimized. So what is normally done, you cover some parts in that it will react with others. This is where this principle comes in, reducing derivatives. In that process, as I've been explaining, of attaching, removing to get your desired compound or product, it will create other derivatives from the process, because we are masking, we're adding groups that will mask some parts of our product or a simple starting compound. This, in other words, would require to use other processes to get rid of them, hence generating more waste. So better to use enzymes to break down or to react with this compound in order to achieve a particular product. Referring to one of the previous videos we did, we saw that the biological catalysts known as enzymes that are very specific in this regard, they should be employed because they will attack a particular site that is desired. This is because enzymes are selective. They will react with a particular site, not the whole compound as a whole. We'll use a typical example of the manufacturing of the antibiotics based on penicillium, or replacement of the classical chemical enzymatic process whereby the 6-aminopenicillinic acid is obtained by reacting the catalyzed immobilized enzyme penicillin amide. This process will help to minimize process requirements. For example, the negative 60 degrees in the former reaction, whereby I would have saved on energy. So we are seeing, using such ways, we would have saved not only on the longer processes that would be involved, but also on energy. With all of this knowledge around, we shouldn't get tired to learn more about what is being done, what is the best practice, because day by day, greener solutions are being made, greener solutions are being advocated for, and there is research in this paradigm. This is a critical call to researchers, manufacturers, different scientists around the world that we should think of making the processes greener. And so keep going, keep researching for the best, and never know what may seem hard to replace today. Someone may have found out a way to do it greener. Thank you for watching.